Okay, so this video is going to focus on how we can apply thermochemistry to IMFs and how we can look at them in terms of particle diagrams. And the place where most of the time this gets applied is to the lab that's actually mandatory in AP chemistry. And that is the one where we look at the heat that's given off to the solution when we dissolve salts. So some salts are endo, some salts are exo, and we can look at this in terms of the calorimetry data and calculate delta H of a reaction. And there were previous videos dedicated to that. But in this case, we want to look at IMF energies. Okay, so kind of like bond energies, but for the IMFs. And so we're going to take a look at LIF dissolving into water. So when this dissolves into water, this starts as a solid, it's in a lattice, and it goes to Li plus F minus. We don't include the water because the water doesn't change in the process, and both of these are aqueous. And so when we draw a particulate diagram for these, we're going to have to show some different components that happen, not as they happen in real time, but in terms of the total energies involved. And I'll show you what that looks like. So I'm going to clear the screen. And we're picking just LIF as an example, but you could do this for any salt. And so LIF is pretty simple because it is, you can pick this, let's see what shape we got here. Okay, so we have circles. All right, so we are going to first draw a lattice. So we have, this is going to represent our Li, and then this is going to represent in blue whoops. So we have Li plus and we have F. Okay, so I'm going to define these really quickly. So this is our Li plus, which is smaller because it is a cation and it loses an entire shell and it has increased Coulombic attractions. We can go back and look at our trends notes for that. And then this is going to represent our F minus, which has not lost a shell, but it's filled its shell and it has weaker Coulombic attractions to pull that shell of electron in because it has a lower effective nuclear charge because it has 9 protons, but 10 electrons to hold on to. So generally, cations get smaller and anions get bigger. That's the general trend. And we know when we have a lattice, we don't just have one of these, we have many of these. So, okay, so we're going to put around each one of these a okay, and hold on a second, I'm going to replicate these. Okay, so I did a little bit of drawing. So if we look up here for the LAF, so if we remember, this is in solid form, so it's actually LIF put together when we start, right? Because we're starting with a solid, we're starting with water, and then we're dissolving. So the dissolved solid is our product. So up here, our IMF is ion-ion. This is an ionic lattice. That's what we call it when it's in the solid state. And it goes plus, minus, plus, minus, plus, minus. It makes a very rigid, very structured solid. And so that's true for all ionic compounds. If we look down here, our other reactant is water, because water initially is just distilled water, so it's just water by itself. So we remember that the hydrogen has the positive dipole, and the oxygens have the negative dipole, and so they're attracted to one another. So you always want to make sure it lines up with the hydrogen facing an oxygen, and this IMF would be hydrogen bonds. So when we talk about this in terms of thermochemistry, what we need to realize is what needs to get broken and what needs to get formed. Well, in order for water to come and make new IMFs with the lattice, several of these not several, but a lot of these water IMFs are going to have to be broken. Obviously, we don't have three waters. We have millions and trillions and trillions and trillions and trillions of water molecules in one cup, but we're just going to represent a few here. And so if we were talking about this actually happening over time, this would happen piecemeal. So maybe this one would break and break off just this little part of the lattice, like right here. And also the lattice would be trillions and trillions and trillions of these ions. So we're just showing a very small representation. We do this in terms of thermochemistry. We don't do it over time. We do it over just showing what has to occur in order for the new things to form. So what we will actually show is in order for this process to take place, what do we have to break? So if these are our reactants, we're showing here what has to get broken. So where I have this line, this is what has to be broken in order to have things available for new things to get formed. And again, it's not like all of a sudden all the ion IMFs just automatically break each other. There's an interaction between these two, but we're not talking about the interaction. We're just talking about what has to get broken in terms of the net loss and the net gain of IMFs. So when we do this, all we basically do is we're going to show our ions, but now they're not going to have any IMFs. So we're just going to simply have, so we're going to break the IMF. So we will just we'll try to make it about the right size here and fill this in with pink. And then we have our, and so we have our blue, and this is our F minus. Fill this in with blue, okay, about the right size here. And so now what do we not have? We no longer have the IMFs connecting this to make this a lattice. These are just ions floating around. And right now they're not floating around in water because we haven't made any connection to water. We've just broken them. And would this ever just happen on its own where it just break? No, we're just showing what gets broken in the process. So these are more theoretical instead of the step-by-step which take place. And obviously we will need to make some duplicates of these because we need to make sure we have the right amount. So we've got duplicate these. So we've got, and now they don't need to have a specific, order anymore. We need two more of these. Okay, so they're no longer bonded. They're free to move around. Okay, and we're going to need three more of these. Okay. And one more. So our first step, I kind of cut off that little tail in there, okay, is to show what is broken because reactants have to break before products can form. What we would do over here with the waters is we'd show the three waters, and obviously there'd be a whole lot more than three. You just have to show a representative amount. So see if I can get some water here with not too much of the. All right, that's pretty good. So let's see, we'll get three of these, and these no longer have IMFs, so this also would have to be broken. So when you describe this, you want to explain how the first step is that you have to break the ion-ion IMFs, and you have to break the hydrogen bonds within the water. And once we have these broken apart, so this would be showing what we have initially. So this is number one is what we have initially. Two is what gets broken, and then in step three is going to be what is formed. And I need to clear some space. Okay, so I've cleared some space just so I've moved everything that was on frame for part two, where we've broken everything over to this side so that we have room for part three. So for part three, what we're going to see happen is, well, now if we've broken everything apart, these are now going to merge and are going to form new IMFs. And the reason why all of these steps are going to be so important is because we can talk about the energies involved in a second. So if we go to step number 3, now what has to form? Okay, so I've made a little table here. So in total, in between steps 1 and 2, we had 2 broken IMFs. And we remember that it takes energy to break bonds or IMFs, which makes them endothermic, which is a positive delta H. And those two combined are ion-ion IMFs and the hydrogen bond IMFs with the water. So the lattice and the hydrogen bonds within the water. And you can add those together to get the total value for everything that's endothermic in this process. And we're going to come over to the other side and we're going to see that the formed IMF, so this would be in the product. So this is what we make, okay? Because if you're making something, that makes it a product. This would be energy that's released, which is exothermic, and that was the ion dipole. In this case, all we created was ion dipole, and that is our total negative H value. So when you dissolve a salt, because these will always be the three places where energy transfer takes place, you can have values which are endothermic. And if your overall delta H for the reaction in this case is 4.73 kilojoules per mole. And I know this because there's a table value of these that you can look up online, or you could have found this out through a calorimetry experiment. But so this is the value specifically for LIF. And so this is 4.73. That's a given value on a table that you can look up in a textbook or online. And what this tells us is that this overall process is endothermic. So what does that mean applied to our values in this little table that we created? What this tells us is this total value of the things that are endothermic, if we take the absolute value of this, the line absolute value, has to be bigger than the absolute value of the exothermic things, because in total, it took more energy to break bonds than it did to form bonds, because overall, this is endothermic. So that would be your bigger value. Those two in combination, the ion-ion and the hydrogen bonds. Now, obviously, that's not the only value. You have to take into account all, but these must be bigger. So this is a greater than sign. If you had a reaction that was exothermic, which in this case it's not, but if you have one that was exothermic, it would be the opposite. The ion dipole value, the absolute value, would have to be greater than the ion dipole and the hydrogen bonds, because if it's exothermic, the exo factor has to be bigger, so that in total you get a negative value. And so this will get applied to several AP problems. So sometimes you're asked to draw the IMFs, sometimes you're expected to explain them, but they're basically just testing, do you understand the premise? When you break an IMF or a bond, it takes energy, that's endothermic, you have to put energy in. And when you form new IMFs or new bonds, intramolecular bonds, it releases energy, and that's exothermic. And so reactions often will involve both forming and breaking bonds. So in net, the overall delta H for the reaction is taking those two values and subtracting them. That's our basic principle when we use delta H for reaction equals, so this is like a visual version of products minus reactants, showing those actual IMFs. And in many reactions, it's very hard to illustrate this because there's IMFs, intramolecular bonds, there's a lot of things going on. So this is one of the most common examples with dissolving, because the IMFs involved are pretty straightforward, and they're ones that AP can expect you to know. All right. Thank you for listening. And the last series in these videos for 5A, will be connected to a little entrance question, and it will be related to how we can actually use delta H as stoichiometry.